The focus of our last unit was on generally looking at oxidation of alcohols and talking about what types of functional groups we achieve through oxidizing alcohol groups. And you can see here an overview of those reaction types that we talked about, where we were oxidizing primary, secondary, or tertiary alcohols to give a variety of different types of products. The thing that all of these reactions had in common was that each of them resulted in replacing a carbon-hydrogen bond from the starting material with a new carbon-oxygen bond in the product, so that the octet was allowed to be maintained for the carbon. In this unit, what we're going to focus on is what specific oxidizing agents we can use. So we're going to be filling in these question marks here with specific chemical reagents that we can use to execute these reactions in a lab setting. Let's go ahead and get started with looking at those reagents. As we think back to general chemistry and what we know about oxidation and reduction reactions, or so-called redox reactions, one thing that you've likely heard before in general chemistry is that in redox reactions, what happens is that during the oxidation of one molecule, another molecule is reduced. Or in other words, as one molecule gains electrons, another one is going to lose electrons during that process. And so what will happen is that the oxidation of an alcohol is going to necessitate that the oxidizing agent during that process gets reduced. So in other words, the oxidizing agent will go from a relatively high oxidation state to a lower oxidation state. So for example, the oxidizing agent could be going from, for a specific scenario, chromium-6 to chromium-3. So in other words, the chromium is getting reduced during that process because it's going from a higher oxidation state, a higher positive charge, to a lower positive charge, meaning that electrons are being gained during that process by the chromium. And as a consequence of that, the alcohol molecule is getting oxidized. So the thing that we're going to see that is true for all of the oxidizing agents that we are going to look at here of alcohols is that they will all have an element that is in a high oxidation state that's directly bonded to oxygen. That oxygen is going to be donated in to the molecule during the oxidation reaction. So as we think about oxidizing agents of alcohols, the commonality that we're going to see is that high oxidation state. So some examples of oxidation states that we will encounter include the chromium-6 that we saw up top there, so I'll just put Cr6+, manganese, Mn in the 7+ oxidation state, and even chlorine in the 1+ oxidation state, which represents a high oxidation state for that particular element. So we're going to see a variety of different combinations of having these elements bonded directly to oxygen. All of those are going to act as oxidizing agents. So the reason why we have this high oxidation state here is that we keep in mind that during the oxidation of an alcohol, the oxidizing agent has to be reduced. It's going to gain electrons to lower its oxidation state. So what we'll see happening is analogously to up top with the example of chromium. During the course of these alcohol oxidizing agents acting to oxidize alcohols, they themselves are going to end up being reduced. So the chromium, for example, goes from chromium-6 to chromium-3 during the process of acting to oxidize alcohol. So these oxidizing agents are going to get reduced during the course of that, and that's why they have to start with a high oxidation state. We can look at specific examples of how we incorporate these high oxidation state elements that are bonded to oxygen into oxidation agents. So some examples include a variety of different chromium-6 reagents. So pretty much if you're looking at a problem and you see chromium in the 6 oxidation states, we can expect that an oxidation reaction is going to occur. A couple of examples would be CrO3, which we'd expect to have chromium in the 6 oxidation state, or alternatively sodium dichromate, which has the formula Na2CrO3 as its formula. In either of these cases, Na2Cr2O3 or CrO3, they're both going to act to enable the oxidation of alcohol molecules. We can also similarly carry out oxidation with potassium permanganate, KMnO4. If we were to look at the oxidation state of our manganese, within that we would see that it's manganese 7+. And then a very cheap and highly effective oxidizing agent is simply bleach. So bleach has the molecular formula NaOCl, or sodium hypochlorite if you want to be more technical in terms of the scientific name. So NaOCl, just commonly referred to as household bleach. And this is in fact how bleach is able to disinfect substances and surfaces, is through oxidation reactions. It will really oxidize like crazy the molecules that it comes into contact with, and therefore enable disinfection of surfaces. It kills cells as a result of that property. So if we take any of these reagents, these oxidizing agents, and we use them in conjunction with alcohols, we can predict what product will form by using that guideline that we looked at the beginning, where a primary alcohol gets oxidized to an aldehyde and then to a carboxylic acid, or a secondary alcohol gets oxidized into a ketone. So let's take a look at this by doing an example problem. We begin with sodium dichromate reacting with our primary alcohol ethanol. We're asked to predict the major final product of this reaction. As we think about oxidation, which is what the lines of thought that you need to be going down, recognizing that we have a high oxidation state element in here, and particularly chromium is really commonly used for oxidations. So we need to be thinking about oxidation, and when we oxidize an alcohol, this is a primary alcohol because we have just one bond between the alcohol carbon and another carbon, and two bonds between that carbon and hydrogen. What we can do is replace each of those two carbon-hydrogen bonds with carbon-oxygen bonds. So what we would think about here for the oxidation of this molecule is that we would first replace one of the carbon-hydrogen bonds with a carbon-oxygen new bond to take us from this primary alcohol to an aldehyde molecule. So we went from a 2-carbon primary alcohol to an aldehyde. Our aldehyde then, you'll notice, still has an available carbon-hydrogen bond here at that reactive carbon. The reactive carbon is the one that's bonded to the hydroxy group to start with. And so we can further oxidize from there to convert into the carboxylic acid. So we're following here the general template that primary alcohols get oxidized into aldehydes, and then aldehydes get further oxidized to give us the carboxylic acid product. So we've made another carbon-oxygen bond right here. So we ask the question, is the sodium dichromate going to take us from the primary alcohol to the aldehyde, or would we end up in the reaction flask with the carboxylic acid? The answer is all of the oxidizing agents that we've talked about above, including the chromium-6 oxidizing agents we mentioned, the potassium permanganate, and the bleach, are all going to take a primary alcohol and typically oxidize it all the way to the carboxylic acid as the final product that you would observe in the reaction flask. And the reason for that is aldehyde molecules that we have as our intermediate here tend to be even more easily oxidized than alcohols, and so as a result it's challenging to stop at the aldehyde here without going all the way to the carboxylic acid product. So in general, what will happen if you use any of the reagents up top is that they are all going to oxidize primary alcohols all the way to the carboxylic acid. The carboxylic acid is the end of the road because the reacting carbon atom no longer has any hydrogens directly bonded to it. So we can write up here as a general rule that each of these three types of reagents that we looked at here will all take a primary alcohol and through that oxidation reaction convert it into a carboxylic acid. Now, what if instead we started with a secondary alcohol? We have less carbon-hydrogen bonds available in a secondary alcohol, so let's see how that would impact the outcome here in a second example problem. So for our second example problem, we'll take a secondary alcohol. Isopropyl alcohol is the common name for this, which you very likely have in your medicine cabinet. We take any of these oxidizing agents that I put in the red box up there up top. So we could just take isopropyl alcohol from the medicine cabinet, mix it with bleach, also likely available somewhere in the house. That's going to result in oxidation of the alcohol group, that carbon atom in particular, and that will replace the carbon-oxygen single bond with a carbon-oxygen double bond. We will always be taking a secondary alcohol and oxidizing it to a carbon-oxygen double bond of a carbonyl. So that's going to leave us then with a ketone as the product of this reaction. And we think about, can we oxidize any further using bleach here after we convert the alcohol group into a carbonyl group? And the answer is generally not so much. So we're going to put down no reaction here. So the final observed product here would be the ketone product. The reason we stop at the ketone instead of oxidizing further is our carbonyl carbon here has no hydrogens directly upon it, so there's no carbon-hydrogen bonds that we could replace with carbon-oxygen bonds, and therefore the reaction stalls there. And just a little bit of a fun fact here, this particular ketone that we've created would have the common name acetone, and you may recognize the name acetone as fingernail polish remover. So if one were trying to do some at-home chemistry to make fingernail polish remover, taking bleach and mixing it with isopropyl alcohol would do the trick. Not advisable to try that at home, but that's what the reaction would yield here. We could also look at this for a tertiary alcohol example problem. So we'll take our tertiary alcohol, mix it with any of the 3 types of oxidizing agents that we've listed up top there. So I'm going to use tert-butyl alcohol, and this is my example of a tertiary alcohol. I'm going to mix it with the only oxidizing agent we haven't used so far, potassium permanganate. And you would expect here that there would be no reaction take place, because if we take a look at the carbon atom that has the hydroxy group bonded to it, that's going to be the carbon that's susceptible to oxidation reactions. That carbon has no directly bonded hydrogens, and therefore there can be no reaction, because the oxidation reactions rely on taking away a carbon-hydrogen bond and replacing it with a new carbon-oxygen bond.